Hope you guys are ready for this miniature class coverage. You guys took already a class upon this of viscoelasticity, so I will test your knowledge, what you guys learned in class and everything. Sijun, can you stop being on your phone, please?
Sorry.
Yeah, thank you. I would not like to see you on your phone again. Keep that clear. All right. So, what might you guys be able to? What does the word viscoelasticity mean? What would you think the two main effects are shown by the viscoelastic materials?
Viscosity and elasticity.
Absolutely.
The term viscoelasticity consists of two main keywords: viscosity and elasticity. Elasticity is usually the tendency for a solid to return to its original shape after a deformation occurs. These materials tend to store all the energy from the applied stress and use it to recoil back to its original shape. Viscosity, on the other hand, is the material's resistance to flow. When a stress is applied, all the energy received from the stress is dissipated in the form of heat, and that's why it flows. So now, how can one use both of these definitions to define viscoelasticity? So, viscoelastic materials under a deformation get to store some of the energy given by the deformation instead of dissipating it all as heat. This allows the material, after the deformation occurs, to recover some of its deformation. So therefore, this material tends to show both viscous and elastic behaviors. So, students, now we begin the assessment of your understanding of viscoelasticity. You will be tested on 4 different videos, each one representing either a quiz, a midterm, or a final. And you will be required to answer some questions related to the video. Now we will start off with the first assessment, the quiz.
Oh, I need some energy. Where's the food at? I need to go to the kitchen. What do I have today? Oh, eggs! Nothing better. Am I gonna eat a sunny side up egg today or an omelet? This microwave egg omelet cooker might give me both options. Let's see. Hey there, how's it going? Did you guys ever see this invention? I can either make my eggs an omelette or sunny side up. Wow, I have a lot of work to do today. All of these aging experiments. Egg whites. Might just keep the yolks in them today. Can't wait for this omelet. Oh, look at that. I need myself some milk. I'm really thirsty.
Hey, Amer.
Oh,
so
hey.
many drinks.
You're thirsty too?
Yeah, can you give me one? How about this one?
Oh, no. I'm saving this for Friday. You can grab one of the other ones. How about grab this one?
Oh, okay, thank you.
I'm gonna grab this. What a good meal. Wow, that egg was really good. To wash my hands. Oh, that's peppermint. Ooh. Well, students, now that we've watched this first video related to the quiz, what phenomena did you guys recognize that was related to viscoelasticity? There was, I think I could think of two, but did you guys recognize them?
The extruded swell from the soap bottle.
Yes. Good eyesight. Good job.
So
Does anyone think of?
when you're cooking the egg, is kind of like a tubeless effect phenomenon.
Yeah, the tubeless siphoning. You are correct too.
So why would these phenomena occur with viscoelastic materials? The tube siphoning phenomena is caused by viscoelastic stresses. These viscoelastic stresses usually result from the stretching of the polymer-like molecules in the solution. The stretching of these polymer-like molecules in the solution allows the viscoelastic stresses to overcome the weight of the siphon jet against the gravitational force and forces it to be intact. This stretching gives rise to viscoelastic stresses, which remember the deformation history of the fluid as it flows through a tight orifice. Towards the exit of the orifice, the chains begin to recoil, and we can then witness the swelling of the fluid. Now, it's time for your first midterm. Listen carefully.
Hey, Asijo.
Hey.
I realized that you were in a hurry today morning. What was that all about?
Yeah, I have a very important homework due tomorrow today morning.
Oh,
So
okay.
I'm pretty in hurry. And you know what? Today is really my bad day. When I drive this morning, my car just passed by a speed bump and I hit my head. That's very hurt.
Oh,
my
wow.
God.
Which
Yeah.
speed bump was it? Was it the one by Chili's?
Yes, exactly.
Oh, that speed bump. Tell me about it. I think it usually comes down to the suspension in the car.
Yeah.
You see, the suspension is made out of two key components, the spring and the dashpot. And whenever you have both of these mixtures, they're supposed to absorb any bumps or any shocks that happen. But that speed bump, I've been there, I can see. And I got my head beat up too.
Yeah.
Okay, students, after now we finish this watching the video on these two students conversing, you guys went over a couple of models in the viscoelasticity class that you guys just took, and I was wondering if you have recognized any of the models that if you have recognized what they talked about in terms of a model. Does anyone have any idea? Do you guys understand like there was a model being talked about in this video?
Maybe Maxwell?
Absolutely, yes, there is a Maxwell model. And that brings me to the second question. How does this model work in viscoelasticity?
So the Maxwell model will have a dashpot and a spring. So like in this video, when there is a shock, the energy will be absorbed by the dashpot.
Okay, thank you very much. You're actually correct.
I will use the help of a video to hopefully clarify how a car suspension system works. A car's suspension system usually consists of two important equipment, a spring and a dashpot. Both of these equipment have the ability to withstand either a shock or a bump. The spring usually stores all the energy it receives, and the dashpot usually dissipates most of the energy it receives in the form of heat to the surrounding oil. As demonstrated in the video, the response of a car's suspension does not differ whether the car is passing over a bump or whether the steering wheel is turned. Both the spring and the dashpot help with minimizing the shock effect by the storage and the dissipation of energy. This idea of combining a spring and a dashpot together was the basis of viscoelastic models back in the time.
Another method of understanding a polymer's behavior is the spring and dashpot model. The spring represents the elastic behavior of the polymer. The elastic portion of the model acts as a metal and has fully recoverable strain. The dashpot represents the viscous behavior of the polymer. The viscous portion of the model acts as a fluid and has unrecoverable strain. One way to understand the spring and dashpot model is by examining the behavior of the system with a suspended load. A graph of deformation and time helps you understand the mechanics of the system. The first component of the model is a spring. When a weight is added to the spring, an immediate deformation is observed. When the weight is removed, all of the elastic deformation is recovered. The second portion of the model involves a spring and dashpot in parallel. The spring portion of the system cannot immediately deform because the viscous component slows it down. Therefore, the deformation takes place over a period of time. As the weight is removed from the system, the deformation recovery of the spring is slowed by the dashpot. The third component of the model is the dashpot. The dashpot flows while the weight is applied to the system. When the weight is removed from the system, none of the viscous component is recovered. To fully understand the model, the three components must be superimposed. When the weight is applied, the system undergoes an immediate deformation due to the spring component. The second component, with the spring and dashpot in parallel, produces a deformation over time. The viscous deformation of the third component is added to the second component. This results in a model of the behavior of the loaded system over time. When the load is removed, the initial deformation of the spring is recovered. Then the deformation of the spring and dashpot is recovered over time. The deformation of the dashpot is never recovered. The result is a permanent deformation of the system.
As described in this video, we can use spring and dashpot to describe the viscoelastic behaviors. In this course, we have learned two basic models, namely Maxwell model and Qian model. So the picture on the left shows a series of spring and dashpot, which is Maxwell model. The picture on the right hand shows a parallel combination of spring and dashpot, which is Qian model. In real situations, although the Maxwell model is conceptually reasonable, it cannot fit the experiment data well. Instead, we need to use generalized models. The picture on the left shows a generalized Maxwell model. It's a series of Maxwell elements. The one on the right-hand side shows the generalized Qian model. It's a series of Qian elements. So now we have learned all these models, but how to use them in real situations. We should choose a best one based on the materials and the properties that are being observed. And you should notice these models are not perfect, so we still need a general approach.
Now that we are done with the quiz and the first midterm, let's watch the video for the second midterm.
Safety is a priority. So can you give me again your address? So we can
1100 4th Street.
1100 4th Street. Alright, it's ready. Do you have a GPS by any chance in your
we're seminar
car? Oh, okay. I don't know, I had a couple of issues with it, but I want to hear if you had the similar issues. And
Yes. I feel it's like quite disturbing in the summer, especially like in Naboka, because the temperature gets very hot.
Tell me about that, yeah?
Yeah, it falls off very easily.
Oh, yeah, that's exactly what I'm experiencing, actually. I don't know, I'm thinking of investing in a newer one, actually. So, students, we saw a couple of things in this video, and I think there was a couple which were related to viscoelasticity. So I was wondering if you guys did realize or recognize anything that was related to viscoelasticity in this video that we just watched.
The GPS holder, it has a rubber part of it.
That's a very, very good answer. I think you're in the lead right now with the score points, huh? Someone's getting any.
Not anymore. How about the brakes in my car?
Absolutely correct, Mr. Shurian. Yeah, you're tied. Both of you guys are tied. So now that we went over those two things, that brings up another question, which relates both of the phenomena we talked about in the first question. So how does the temperature affect rubber?
I think when you hit the rubber, it shrinks.
Oh, okay, that is true. That is absolutely true. So Qian is coming back in the race now, so yeah, should watch out.
The reason why the GPS holder sticks to the surface it is attached to is due to the pressure difference formed between its vacuum and the surrounding atmosphere. The material that constrains the vacuum from the atmospheric pressure surrounding it is a rubbery material, whose behavior is strongly dependent upon temperature. Therefore, when the temperature increases, the entropy also increases, and in a rubber's case, maximum entropy is at its unstretched form. The reason that a vacuum does occur is because of the rubber's ability to stretch, but as temperature increases, the rubber tends to shrink, causing the GPS holder to fall off place.
Now, when the rubber will shorten when heated, what will happen if the rubber gets cooled down? Let's watch your video.
We have two rubber balls, similar in appearance but of different compositions. The ball on the left is neoprene rubber. The ball on the right is a proprietary polymer which is near its glass transition temperature at room temperature and absorbs kinetic energy when bounced. If we cool the ball on the left and heat the ball on the right, observe changes in their elasticity as a function of temperature. The ball on the right, which did not previously bounce, now bounces slightly after being heated, behaves more like a rubbery elastomer. Ball on the left, which bounced like a rubbery elastomer at room temperature, still bounces after being cooled in liquid nitrogen, but it sounds quite different, like a marble hitting the table. It is now below its glass transition temperature and hence behaves like a glass. If we warm this ball up, see that it viscoelastic response diminishes as it approaches its glass transition temperature until temperature just slightly below room temperature, it behaves like the ball on the right-hand side did originally.
Here, we will introduce a concept, glass transition temperature. Similar to the melting temperature, polymer has a specific property, glass transition temperature. Above the glass transition temperature, the material behaves more rubber-like. Below the glass transition temperature, material behaves more glass-like. So in this video, there are two materials. The rubber cooled down to a temperature below glass transition temperature, so it behaves more glass-like, while the other material heated to above glass transition temperature. It behaves more rubber-like.
In this video, the effects of increasing pressure upon silly putty, a viscoelastic material, is witnessed. We can see that the material flows under pressure, which shows its viscous character. When the deformation has occurred, we realize that the material remembers its shape before deformation and slightly recalls back. This shows the elastic character of the material.
Since temperature and pressure can affect the viscoelasticity a lot, we can take advantage of them in experiments. In this plot, x-axis shows the time scale of the experiment. Towards your left, you will notice that the time is very short. This might be beyond the instrument sensitivity. Let's look at the next plot. The different temperature shows different behaviors in the same time scale. So that's interesting. And if you look at them carefully, you will notice that this plot is actually organized. Here, we will introduce a concept, namely time-temperature superposition. The relaxation function doesn't change shape with temperature, but does change position in time. So, high-temperature short-time experiments, therefore, are equivalent to long-time experiments at lower temperature. So, if we shift the curve one by one, we will eventually get a master curve. That's exactly what we want. And this principle can be used as a powerful tool to describe material behavior outside of the normal experiment window. Pressure has a similar effect. Low pressure, short-time experiments are equivalent to long-time experiments at high pressure.
Another two important properties that determine the behavior of viscoelastic materials are the molecular weight of the material and the entanglement between chains of the material. As the molecular weight increases, viscosity also increases, indicating that the material is becoming more solid-like. Whereas, when the number of entanglement between chains increases, the material is going to act more elastic-like. Now it is time for the final assessment. Let's watch this final video and make sure that you'll be able to answer the final questions.
Have you ever had any cinnamon rolls?
Yes, I actually enjoy them.
I'm actually creating some cinnamon rolls. Might there be some here in the house?
Unfortunately, we don't have it now. If you want to try, maybe we can try to make it. Have you ever made it?
No, I haven't. Might you know of the recipe by any chance?
No, maybe you can search it online.
I think that would be really helpful.
Yeah.
Let's enjoy some cinnamon rolls.
Sticky buns are a bakery bestseller, and it's no wonder. They're made of rolled leavened dough and filled with a sticky sweet filling. But let's start with the classic cinnamon sticky bun so you can get a handle on the basics. Now, it starts with a soft dough. And part of what makes a soft yeast dough is actually the dairy component. In this case, I've got 1.25 cups of 2% milk. And the last ingredient for the dough is 3/4 teaspoon of salt. I'll use the hook attachment, making the dough nice and stretchy. You know when you can see the dough climb the hook? That's when you know it's properly kneaded. It is an easy to manage dough. It's so soft and silky. I like to shape it into a nice ball before I let it rise. Take a big bowl and I just give it a light coating of oil. And then what's important is that you cover the bowl completely with plastic wrap to protect the dough so it doesn't dry out on top. Now what you want to do is put this in a warm place, and it takes 90 minutes to 2 hours for it to double in size before it's ready to roll and fill with the sticky filling. And now it's time to get rolling. I have a batch of the yeast dough that has risen for the 90 minutes, and it has actually doubled in size. And turn the dough out, little sprinkle on top, and roll this out into a rectangle. It rolls out so easily. There we go.
Are you ready for this? Some cinnamon rolls?
Oh, I'm sorry, I don't have all the ingredients, and I think it's too complicated for me. You know, I'm only a beginner for cooking. But I can cook you some spaghetti. Do you like spaghetti?
Spaghetti? I guess.
So, students, this is almost it. This is the final video, and you have just watched it. So, after watching this video, did you guys see any phenomena related to viscoelasticity in this one? This is where you should rack up some points, so.
I see the viscous flow.
That is true, that is true. What else do you guys see? Anybody?
Rock climbing?
Yes. That was a very, very good answer too. So, one last question about the final is, how would you explain both of these phenomena? You want to try? Maybe get in the lead?
I think the viscous flow is because the dough is constrained in the ball, so when you release it out, it flows. And for the low climbing, I guess it's because like it's too viscous, so it like polymer is like the low climbing.
Climbs up the rock. Yes, that is true. That is true. So, seems like Qian's in the lead right now.
I bet you guys are wondering, why does this occur with viscoelastic materials? Well, the rod climbing phenomena occurs when a viscoelastic fluid is stirred using a cylindrical rod. The fluid begins to climb the rod as long as there is continuous rotation. While in rotation, viscoelastic forces are generated as a consequence of the stretching of the polymer-like molecules in the viscoelastic fluid. These forces result in a net positive normal force that causes the fluid to climb up the rod. Eventually, though, the mass that has been forced up the rod relaxes and overcomes the normal forces pushing it up. This explains the instability in the shape remaining at the end of the video.
So, class, unfortunately, we came to an end with this review questionnaire, and it seems like Qian is the leading winner right now. But I think, well, let's give it a round of applause for Qian first. Okay, so much competitive spirit right there. But I'll give both Siju and Shreya a chance to maybe overtake Qian if she doesn't answer first. And the question is as follows. Would you guys recognize any other viscoelasticity phenomena in your daily life?